Yeah, so the last speaker of today is Garret Alston from University of Oklahoma, and he's talking about potential functions of non-exact fields.
Thank you.
You have to.
Okay, I'd like to thank the organizers for inviting me. So what I wanted to do today is talk about some work in progress joint with Conan Leung. And this is some work based on some ideas in this paper by Oganagic, Ekholm, Eng, and Vafa titled Topological Strings and Demodel. So this is based on some ideas of these four people. And basically what I want to do is talk about full name. So basically what I want to do is talk about an A-infinity formulation of some ideas in this paper. So let me first start out by describing very briefly the idea that I want to talk about. So this is some motivation. So what they do is you start out with a knot, let's call it K as a knot in S3. And then associated to this knot, you can cook up a differential graded algebra. It's actually the Legendrian DGA of a certain Legendrian, which I'll talk about in a little bit. But they cook up some differential graded algebra. A has some differential D. And then associated to this, they get some algebraic object called the augmentation variety. So there's some one-dimensional complex variety, and then they say that this is cut out by a certain polynomial. That is, it's cut out by the equations P equals D dW dx, where the W is a certain function. It actually turns out to be the open Gromov-Witten invariant of a certain Lagrangian filling of the Legendrian. So W is open Gromov-Witten potential of a certain Lagrangian filling. And today what I want to talk about is A-infinity formulation of this. So I give A-infinity formulation of this. One of the things we'll do is give a precise definition of this potential function in terms of the A-infinity structure of the Lagrangian filling, and then under some assumptions, we'll show that a certain variety is cut out by this type of equation. Okay, so let me start by describe this. Let me tell you what the setup is. Okay, so the first thing is we're going to have a knot, oriented knot K contained in S3. And then we're going to look at a couple of manifolds. So one thing we'll look at is the cotangent bundle of S3. And I'll draw it like this. So actually, we'll look at a compact part of the cotangent bundle. Let's look at a 3-ball 3-ball bundle inside the cotangent bundle. Let's call this X. So X equals 3-ball bundle contained in T star S3. So that's supposed to be this picture right here. The boundary of this is going to be a sphere bundle inside T star S3. Topologically, it's S3 cross S2. So the boundary of this, we'll call it V, topologically is an S3 cross S2. This thing right here is supposed to be the S3. So you can think of this as S2 cross S3. Okay, so we're going to take this, and then we can get a Lagrangian inside T star S3 by taking the conormal bundle of the knot. So I'll give us some Lagrangian inside T star S3. And then we're going to intersect it with this compact part. So that gives us some Lagrangian with boundary, and then we're going to deform it a little bit so that it moves off from the 0 section here, off from the S3. So we're going to take some Lagrangian, we'll call this L delta. So this is going to be a deformation of the conormal bundle. You can think of the conormal bundle as being L naught, so it depends on some real parameter delta. And this is going to be conormal bundle of K intersect this compact piece right here. And then it has the property that for delta not being 0, this thing doesn't intersect the S3, so we moved it off from the S3. So L delta intersect S3 is empty for if we've actually moved it. Okay, so that's one piece of information that we're going to start with. And then what we really want to do is do a conifold transition with this to get a different manifold. So we're going to do a conifold transition. Geometrically, what this does is you can think of it as shrinking the S3 down to a point and then expanding in the S2 direction. The boundary is going to stay the same. So the boundary, we still have S2, S3. Now we've shrunk this direction down to a point, and this direction we put in. Yes, okay, so this is now in S2 right here. Let's call this Y. It turns out that this is going to be a 4-ball bundle contained in the total space of O minus 1 plus O minus 1 over P1. So you can think of this S2 right here as being the P1. And then since this Lagrangian doesn't intersect the S3, it will survive in here as a manifold, and we can move it a little bit so that it becomes Lagrangian over here as well. So the boundary might have to move a little bit also, and so we get some filling of that. So this is going to be some Lagrangian, and we'll call it L, but it's really going to depend on two parameters, L delta and epsilon. So the delta is the same delta as over there. It's going to be Lagrangian with respect to a certain symplectic form. The symplectic form we want to look at, we'll call it omega y epsilon. So I have two parts to it. It'll have some exact part, which we'll call d lambda. Over here, you had the d lambda also. The lambda is like minus p dq. D lambda is just a regular symplectic form, dq wedge dp. So d lambda lives over here also. And then we're going to add on some little piece for that S2 part. So just take, say, the Fabini-Studi form on P1 and pull it back and then scale it by some small amount, epsilon. So you get a one-parameter family of symplectic forms on this space. And then if we move epsilon a little bit, we have to move this Lagrangian a little bit to keep it Lagrangian with a different symplectic form. So this really depends on two parameters, delta and epsilon. Okay, and then the boundary of this thing is what we're going to be interested in. So let's call this lambda. So this is the boundary of L, but it really depends on two parameters also. But write them all the time, but it really depends on delta and epsilon, since boundary delta epsilon. And then we're going to want to look at a certain complex structure. So we're going to take a complex structure which is S1 invariant, and it degenerates along this hypersurface V here in the sense of symplectic field theory. So we're going to take JY. This is going to be a complex structure which degenerates along the boundary V in the sense of symplectic field theory. There's an S1 action on both of these spaces. Here the S1 action is just basically geodesic flow, and that turns into the action of S1 on this complex vector bundle. And this JY is invariant under this S1 action. So our main interest is in this filling L of this manifold lambda. So that's what we want to study. So main interest in this story is we want to view L as a kind of filling of lambda. And notice that if we take both the parameters to be 0, if we take delta to be 0 and epsilon to be 0, then it turns out that this lambda will be a Legendrian inside a contact manifold V. The contact one form will be lambda restricted to V. So remark, we take the parameters to be 0. So look at lambda 0, 0. This is going to be a Legendrian in the contact manifold V with contact form lambda restricted to V. So this lambda for non-zero parameters can be thought of as a deformation of this Legendrian, but it's no longer Legendrian. It doesn't make sense to talk about Legendrian anymore because this is not contact in the case that epsilon is not 0. So it's just some kind of isotropic deformation. Okay, any questions? All right, so that's the setup we want to look at. And now there's going to be a Floer theory assigned to both of these things. There's going to be a Floer theory for the filling L, and there's going to be a Floer theory for the boundary lambda also. So I want to talk about these now. So let me actually talk about the Floer theory of the filling first. I'll spend some time talking about that, and then I'll talk about open Gromov-Wood invariance for L, and then once I finish doing that, I'll talk about how it relates to the Floer theory of the boundary. So for now, we'll just talk about the Floer theory of the filling. Okay, so Floer theory of the filling L. So first of all, we're going to use this special complex structure that we had before. So that's going to be what we use to talk about holomorphic curves. Now for our Floer theory, we need some chain complex or some underlying vector space to work with. We're going to take a de Rham model. So the underlying vector space is going to be differential forms on L. We'll actually take complex valued differential forms. Complex part doesn't really matter until maybe the very end. And we need Novikov ring coefficients also. So we're going to tensor over C with the Novikov ring. Actually, that's a Novikov field. So these are some kind of formal power series in powers of t to some power. Expressions of the form ai t to the lambda I, where ai are complex numbers, the lambda I are real numbers, and they go to infinity. So this is going to be our underlying vector space. MK can take in K inputs, and it has one output. So this is defined using intersection theory, moduli spaces of holomorphic disks with marked boundary points. They have K marked boundary points. Use evaluation maps to pull back differential forms, do some kind of integration over the fiber to evaluate at the 0th marked boundary point. In general, this MK can be decomposed as a summation over beta of mk beta t to the omega beta. This mk beta is just going to be the contribution coming from homomorphic disks of class beta. So beta is going to be in cohomology class or homology class H2YL. And then we weight them with this weight. So actually this here should be the symplectic form that I used over there. So it should be the omega y epsilon. This is omega y epsilon. And then there's some more structure here also. There's going to be some pairing. The pairing is just wedge and integrate. So I have x, y, pair them up to some sign. This is integral over L of x wedge y. This mk beta, if beta equals 0, this reduces to just the de Rham differential graded algebra. So M10 should just be de Rham differential, so up to sign plus or minus d. M2 should be the products or wedge product. And then all other mk's or mk zeros are 0. So mk0 equals 0 for all other k. So this structure, this and the A infinity operations in this gives the structure of the cyclic A infinity algebra. So cyclic is some other property which is important, but I'm not breaking down what that means right here. But we assume it has that. And then there's one other piece of information we want to put in here. So we want to also have something called an m-1. So this is something defined by Fukaya. He calls this an inhomogeneous term. So this is an inhomogeneous A infinity algebra when you include this m-1. And what this m-1 is a count of holomorphic disks with 0 marked points. So just like the other MKs, this can be broken down as sum over beta, m-1 beta, t to the omega y epsilon beta. And the m-1 beta is a count of holomorphic disks in class beta with 0 marked points. And I didn't mention this, but the L turns out to be special Lagrangian threefold and Calabi-Yau threefold. So the virtual dimension of a holomorphic disk is 0 with no marked points, so you should be able to count them. So this is the number of disks, the boundary on L, class beta, so compactified. And we're always going to use this complex structure. Okay, so that is the theory for filling L. So we get a cyclic A infinity algebra on the de Rham model, and then it has this extra inhomogeneous term. So this is going to be our theory for the filling. Okay, so next I want to talk about open Gromov-Witten invariants. And first I want to talk about the compact case. So this is something done by Fukaya, and then I want to talk about how it has to be changed for this case. So actually I meant to say I want to first talk about the case of a closed manifold, no boundary. And then I'll talk about how it has to be changed for this case where we do actually have boundary. Okay, so open Gromov-Witten theory. So this is for, first we'll do for closed L. This is due to Fukaya. So the setup is L is closed, no boundary, compact, special Lagrangian, threefold, and then to such a thing, you have the same stuff that I described over here. So you have A infinity algebra, you have operators in K, you have pairing, and then you have this inhomogeneous term n minus 1. So associated to all this stuff, we define a certain function. So we're going to define a potential function. And it's going to depend on the complex structure. And we have to assume something about the complex structure, which I'll say in a minute. So let's say J is a complex structure. This potential function is going to be a function from the degree 1 part of the floor complex. And really we should restrict to things with positive valuation. So I'll put a plus there to indicate that. So that means that the powers of T in the Novikov ring are all positive. That's what the plus part means. This is something to do with convergence. You need to assume that. And then this will take values in the Novikov field, but the positive part of it. So again, positive valuation part. And it's defined like this. It sends some element x, goes to m minus 1. This is our inhomogeneous term. So this is just a constant. N minus 1 is just some element of the positive part of the Novikov ring. Plus summation k greater than or equal to 0, 1 over k plus 1, mk x, 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 like this. So this is how we define the potential function. And then this has some nice properties. The most important of which I want to emphasize now is that it descends to a function on the moduli space of bounding cochains. So there, Wj descends to a function on the moduli space of bounding cochains. So what a bounding cochain is, it's a solution of the Moore-Cartan equation. So an element of here that satisfies the Moore-Cartan equation. And then moduli space means we should mod out by some notion of equivalence, a notion of gauge equivalence. So this is equal to solutions of Moore-Cartan equation modulo notion of equivalence, gauge equivalence. So this is the moduli space of bounding cochains. And then when you need to assume something on J here, you need to assume that the images of all J holomorphic spheres are disjoint from L. So assuming images of J holomorphic spheres, non-constant ones, are disjoint from L. So generically, this should be true because the spheres should be rigid. They're two-dimensional. L is three-dimensional. We're in a six-dimensional manifold. So generically, this should hold. Okay, so kind of the moral of this is that in the Fukaya category, objects in the Fukaya category shouldn't just be Lagrangians. There should be Lagrangians plus a bounding cochain, and maybe some other data like spin structure and so on. And then what this says is that this function has a well-defined value on that thing. If you pick a Lagrangian in the bounding cochain, this potential function has a well-defined value on that bounding cochain. So this can be thought of as its open Gromov-Witten invariant. So objects of the Fukaya category are Lagrangians plus bounding cochain. Or maybe you should think of it as like gauge equivalence class of bounding cochain. And then you can think of the value of the potential function at here. So this is well defined by this theorem. You can think of this as its open Gromov-Witten invariant. Okay, so that's kind of the moral of this theorem. Let me show you a little bit about some of the things that this counts, so that you can see that this really does mean open Gromov-Witten invariant, or some maybe generalization of that. So you can sort of see part of it right here in the m-1, because the m-1 was a count of holomorphic disks with 0 arc boundary points on the Lagrangian. So you can see some open Gromov-Witten invariance right there, but it also has some extra contribution coming from this part. So let me tell you a little bit about what extra stuff comes from this part. So what does this thing count? What does WJB count? Oh, actually, let me add one thing. The value depends on J. So if you change J to a different J, this may change. And there's some kind of wall crossing formula that tells you how this changes. So let me just point out that it depends on J. Okay, so what does this thing count? So to show you a little bit about this, suppose we have some bounding cochain. In general, it can be decomposed as some sum like this. And then let's look at some classes of beta that are minimal. So suppose beta 1 and beta 2 are minimal. So what this means is that a holomorphic disk in one of these classes can't be broken up into a sum of disks in two other classes. The class beta 1 can't be broken up as a sum of A plus B, such a and B admitted disk. So that's what the minimal means. These are kind of like maybe lowest energy disks you can think of. Then let's look at the contribution to this WJB from each of these things. So this is some element of the Novikov ring, so we can look at the coefficients of the various powers of t. So if I look at t to the omega beta 1, the coefficient is just going to be this m minus 1 beta 1. So that's exactly what probably you'd expect. If I same thing is true for beta 2. But then the more interesting thing is, let's look at the sum of these two things. So say the coefficient of t to the omega beta 1 plus beta 2. So this actually is going to have two different parts contributing to it. So it has one thing coming from the m-1. It'll be m-1 beta 1 plus beta 2. And then it has some other part also. It will be the pairing between b beta 1 and m0 beta 2 of 1, like this. So geometrically, what this is wedge and then integrate. So this is like intersection product. So b beta 1, because b is a bounding cochain, this is some, let's do it like the chain version instead of cochain version. This is some two-chain whose boundary is the boundary of the disk beta 1. So I'll draw a picture here. So this two-cycle right here, not cycle, two-chain, b beta 1, and the boundary of b beta 1 should be m0 beta 1, 1. So this is the boundary of disks in class beta 1. So that's what it means to be a bounding cochain, is the boundary of this chain is equal to the boundary of the disks of class beta 1. So that's what that thing represents. This right here means the boundary of the disks in class beta 2. So maybe something like this. So this is m0 beta 2, 1, and then they have some intersection in general. Say they intersect right there. And that's what this term right here counts. So this is some type of term that will be appearing in not the m-1 part of W, but this higher order part where I have this sum of 1 over k plus 1, blah, blah, blah. So this is a type of term that will appear in that part. Okay, so this potential function is going to include that type of thing. So this gets included in the open Gromov-Witten invariant for this Lagrangian plus bounding cochain. And so this is a very simple example, but there'll be higher order terms like this to all levels. So you can, to organize this, you can think of this term as corresponding to some kind of tree, weighted tree. The weighted tree should be a very simple one. It's just a single vertex, beta 1, associated to it. This one corresponds to single vertex of beta 2. This one is single vertex with beta 1 plus beta 2. And this is the weighted tree with two vertexes and beta 1 and beta 2 assigned to that. And then you get more and more complicated trees, you'll get more and more terms like this appearing. Okay, so that is a review of the open Gromov-Witten invariants for closed Lagrangians. So now let's go to the case that we're interested in. We have a non-closed Lagrangian has a boundary. Okay, so back to our example where L has non-empty boundary. Okay, so we have to make some choices when we define these. So the most important choice we have to make is we have to make some choice of splitting of the cohomology of the boundary of L. So we have to choose actually a Lagrangian split. So I'll phrase it like this. We have to choose a symplectomorphism of H1 lambda. So in the case that we're interested in, this is two-dimensional, so this is just isomorphic to R2. If you take L has H1 equal to real numbers, and if you restrict to the boundary, it embeds as a one-dimensional Lagrangian inside here. So then you can choose a complementary Lagrangian. You get some splitting of this symplectic vector space. The symplectic form here is wedge and integrate. So you have to choose a symplectomorphism that makes this isomorphic to H1 of L plus the dual of H1 of L. So you can think of this as cotangent bundle of H1L. So you have to make some choice like this. And then we want to choose a closed one form on L, generating H1 of L. So this choice doesn't matter so much, but I needed to write down the potential function. So let theta L equal closed one form on L, generating H1 of L. And then, so this splitting right here gives us two projections. Let's call them pi 1 and pi 2. So pi 1 will project to H1L, pi 2 will project to H1L star, but we're thinking of these as Lagrangian subspaces of H1 lambda. So then we're going to define potential function Wjy. So this is going to go from CF1L plus the positive part of the Novikov ring. So it's going to be basically Fukai's potential function. We're going to have to add on some extra boundary term because we have a manifold with boundary. So it's going to be x goes to m minus 1 plus some k greater than or equal to 0, 1 over k plus 1 mk x x x. So this is the same part as before, but then we add on some boundary term. And this boundary term depends on the splitting. It's going to be 1/2 integral over the boundary of L to pi 1 x wedge pi 2 x. So actually, I forgot to mention something. So we don't want to define this on the whole thing. Let's just define this on bounding cochains. So contained inside here, we have the set of bounding cochains. So that's contained inside here. And so we just define this just on the set of bounding cochains. And bounding cochains have the property that if you restrict them to the boundary, they're closed. So they give you cohomology forms, and you restrict them to the boundary. And so then this pi 1x and pi 2x is well defined. That would be well defined in general. So x restricted to the boundary of L, d of it is going to be 0 for x in there. Okay, so then we can prove that with this extra term on the end, this has the property that it only depends on the gauge equivalence class of x. So this descends to a function defined on the moduli space of bounding cochains. So theorem Wjy of x only depends on gauge equivalence class of x. So we get this is defined on moduli space of bounding cochains. And because the cohomology of L is simple, H2 of L is actually equal to 0, and H1 of L is one-dimensional. This means that there's a one-dimensional family of bounding cochains. So fact, because H1L is R, H2L is 0, the obstruction for finding bounding cochains lies in this cohomology group. And because it's 0, that means basically there is no obstruction for finding bounding cochains. There exists a one-dimensional family of bounding cochains. Such that they all are indifferent. None of them are gauge equivalents. So in fact, we can find them of the following form. So in fact, we can find bounding cochains depending on one parameter of this form, S times theta L plus sum over beta B beta. This S is, you can think of it as some kind of holonomy. So we should count these things with holonomy. So this is going to be S e to the S theta L paired with boundary beta, and then T to the omega Y epsilon beta. Okay, so we can find a one-parameter family of bounding cochains of this form. S is a Novikov ring parameter, positive valuation part of the Novikov ring. So these are bounding cochains. Okay, so now we're going to define the open Gromov-Witten potential to be this W evaluated at B of S. So this will be some function that depends on one parameter. And because of this S theta L here, you can think of the parameter as being an element of the degree 1 cohomology. That's a definition. So we define open Gromov-Witten potential function for L to be W, J, Y. So it depends on parameter S. So this is going to be just that W that we defined before, but evaluated at this bounding cochain, B of S. All right, so what does this count? Let me draw a picture to show you what this counts. That'll be analogous to what was counted in the closed case. So what does WJY of S count? So again, just to illustrate this, let's take beta 1, beta 2 to be minimal classes. And then remember, in the closed case, there are different types of weighted trees had different contributions. So you have a similar thing here. So let me draw some trees and then tell you what their contributions are. So the trees we looked at before were these two simple ones, beta 1, beta 2, and then beta 1 plus beta 2, and then a tree like this, beta 1 and beta 2. So these first ones are the same as before. This is n minus 1 beta 1. This is n minus 1 beta 2. But now we should also weight with this holonomy. So this should actually also have a weight of e to the s beta L paired with boundary beta 1. This should have a e to the s beta L boundary beta 2. So the beta 1 plus beta 2 is going to be similar, so I'll skip that. This one right here is going to be the pairing between B beta 1, M0 beta 2, 1. And then this is weighted with E to the S theta L paired with boundary of beta 1 plus boundary of beta 2. So now the picture for this is a little bit different than before. The idea is the same, but now the bounding cochain looks a little bit different. The bounding cochain now is going to stretch to the boundary of a Lagrangian because that's what it has to be to kill the cycle. So it's going to stretch to the boundary of the Lagrangian like this. So this is B beta 1. This part right here is the boundary of B beta 1. So this should be equal to M0 beta 1, 1. This part right here, this is contained in the boundary of L. And then this part right here is M0 beta 2, 1. So we're counting the intersection pairing between these two things. Okay, so my time is floor theory of the boundary et al. But let me very briefly talk about that. So relation to floor theory of the boundary of L. So the boundary of L, this is what we're calling lambda. So there's a floor theory for this. So we call it CF lambda. So this is actually some kind of immersed floor theory. So remember there was this S1 action floating around, and if you mod out by this S1 action, then this will be an immersed Lagrangian in the quotient. And so then you can define the floor theory for this thing. And then this actually has two subalgebras. It has a CF lambda. Let me put a bar over it to indicate that's an immersed thing, quotienting by S1. So this has a greater than part, and this also has a greater than or equal to part. Now this one should be thought of as some kind of dual of a deformation of the Legendrian DGA. So in general, you can think of the dual of a DGA as being A infinity algebra, and it's a deformation of this because this lambda, remember, depending on some parameters, delta and epsilon, if I take those to be 0, I get Legendrian. But if they're non-zero, it's not quite Legendrian, so it's some kind of deformation of that. This has, so think of this as CF lambda bar greater than 0, plus it has some other part coming from the cohomology of lambda. So this you can think of as having something to do with braid chords of positive length. You can think of this as having something to do with braid chords of 0 length. So basically we're doing like Legendrian DGA, but putting extra mark points, boundary mark points, and allowing these marked boundary points to go through cycles in lambda. That's kind of what this thing is. Okay, so then we expect that there exists an A infinity morphism. Let's call it F from the floor theory of the interior to the floor theory of the boundary. And the important thing is that goes into the greater than or equal to 0 part. You can't put the greater than 0 part. You have to put the greater than or equal to 0 part. So you need to allow cycles putting into your mark points. So let's call this, this morphism is F. And so this implies that if I push forward this bounding cochain, this family of bounding cochains on the interior, I get a one-parameter family of bounding cochains here. So this is a one-parameter family of bounding cochains. In CF lambda bar greater than or equal to 0. And now let's project to just the 0 part. Project to the 0 part, so that means project to this cohomology part. So let phi of s equal the projection to this H1, it'll actually be an H1 lambda of F push forward B of S. So this is a one-parameter family of bounding cochains inside H1 of lambda. So it turns out to be some kind of Lagrangian variety inside here. This is two-dimensional, so actually anything one-dimensional would be Lagrangian. But so this, so image of phi is equal to a Lagrangian variety in H1 lambda. And then this potential function that we defined before will be a generating function for this Lagrangian variety. Then WJY is a generating function for this Lagrangian. So in other words, it means that if I pull back the canonical one form PDQ, this embedding phi, then W's potential function is the differential of this potential function is the pullback of this one form. That's what it means to generate this. Okay, so this Lagrangian variety can be thought of as like the dual to the augmentation variety, and then saying that this equation is true. This is the analog of this P equals dW dx that I wrote down at the beginning in terms of this how Aganagich, Ekholm, and Baffa describe this story. Okay, so I'll stop there.
Questions? So in FO, usually the derivative is like more displaceable fibers.
So in I think so what you're describing is a little bit. You're talking about a toric case, probably, right? Yeah. In the setup that I described, if you look at for the closed case, especially Lagrangian threefold, the critical points of the open Gromov-Witten potential correspond to bounding cochains. So critical points are bounding cochains. They may or may not have non-zero Floer theory. And in the toric case, where you're talking about, everything is weakly unobstructed. Right. And then you have a slightly different potential function you look at. The critical points correspond to non-zero Floer cohomologies.
Yeah, yes.
So it's a little bit different of the story.
So here the flow homology is that unobstructed?
So it's unobstructed if there exists a bounding cochain, and there would be, in a closed case, it's a bounding cochain if and only if the bounding cochains correspond to critical points of the superpotential. Yeah, so the critical points of the potential function correspond to bounding cochains. So if there's no critical points, then it's obstructed. If there are critical points, unobstructed.
So what's the flow homology?
That I don't. In the closed case, I don't know if there's any. You can say what it is just abstractly. In this, for the setup that I'm looking at, the Floer, I think the Floer cohomology will just be the same as the singular cohomology, probably, but I'm not sure. I'm not actually sure. Zero. Dimension. Actually, I think you could have some map from H0 to H1. I'm not sure. Yeah, I don't know what it is.
Thanks for speaking again.